Hello everyone, I am Honar Gupta, a PhD scholar at IIT Kanpur. I am TA of the course Fundamentals of Supersonic and Hypersonic Flow. Today we will discuss about the week 4, and if you have any doubt you can ask that. So we'll start. We'll try to solve some problem first. The relation between Nusselt number Nu and Stanton number Ch is given by option A, Ch equal to Nu Re upon Pr, option B, Nu equal to Ch Re upon Pr, option C, Nu equal to Ch Re Pr, and option D, Ch equal to under root Nu Re Pr. So how to solve, what is the relation between these numbers? Here Re is the Reynolds number, Re is Reynolds number, and Pr is Prandtl number. And the Nusselt number is given by Qwx upon Ke TAW minus TW. Where QW is local heat transfer rate, Ke is thermal conductivity at the edge of boundary layer, E is for edge of boundary layer, TAW is adiabatic wall temperature, and TW is wall temperature. Stanton number Ch is given by Qw upon rho E UE HAW minus HW. Rho is density, U is velocity, and H is enthalpy. E is for edge of boundary layer, and W is for wall, and AW is for adiabatic wall. Like I mentioned that W is wall, AW is adiabatic wall, E is for edge of boundary layer, K is thermal conductivity, QW is local heat transfer rate, which is given by energy per second per unit area of wall, which is equal to K rho T upon rho Y W. It means that this derivative is taken at the wall. So how to find the relation? We will take one number. Let's say we are taking Nusselt number first. So Nusselt number is given by QWX KE TAW minus TW. If you see this relation Stanton number, in its denominator there is HW minus HW, which is similar to Nusselt number, because HW can be given by, if we take calorically perfect gas, then HW equal to CP TAW and HW is CP TW. So if we take the CP common, then it's similar to this denominator part. So what we can do, we can multiply by CP in denominator we can multiply by CP in the denominator and numerator, and we need, there are two more numbers we are getting, which is Reynolds number and Prandtl number. And one more thing is that in Stanton number, with this HAW minus HW, there is also rho E UE. So we will also multiply by this number rho E UE also and divide by rho E UE. So if we separate this x also from this, the first term which we are getting is nothing but Stanton number. After separating x, we will get rho E UE x, and if you compare with Reynolds number, what is Reynolds number? Reynolds number at the edge, Reynolds number at distance x can be given by rho E UE x upon mu e. So only thing missing is mu e, so we can multiply and divide by mu e. So this last term we will get is CP mu KE upon KE, which is this KE. We are taking it here, and we know that Prandtl number is given by CP mu e upon KE. Mu CP upon K, you might remember. Now if we multiply this CP inside, then we will get HAW minus HW, and this whole term is nothing but Stanton number CH. This we already saw. This number is what? Reynolds number given by rho E UE x upon mu e, and the CP mu e upon K is what? This is Prandtl number. So we got this mu and U equal to CH RE PR. So Nusselt number can be given by product of Stanton number, Reynolds number and Prandtl number. So which option will be correct? Option C will be correct. Is there any doubt? Now we'll see second problem. Which is in a non-similar compressible boundary layer, the local spring friction coefficient on the wall depends on option A G dash xi 0, B G double dash xi 0, option C F dash xi 0, and option D F double dash xi 0. And where xi is given by integration 0 to x rho e UE mu e dx. So what has been done, that let's say our coordinate system is xy, we have transformed it to xi eta. What is f and g? F dash is given by u upon ue and g is given by h upon h e, where u is velocity and h is enthalpy and e is referring to the age of boundary layer. So we have to find what is the coefficient of friction, or at what function it is depending on. So local skin friction coefficient is given by Cf equal to tau w upon half rho e ue squared, where tau w is what? Shear stress at the wall, and the tau w is given by mu rho u upon rho y w. One thing which I did not tell, this k is also at the wall, so this whole factor is at the wall. Similarly, this tau w equal to mu dou u by dou y at wall. So first we need to find what is it dou u by dou y at wall. Only then we will be able to find the CF. So first, for finding this, we have to know the distance function. We have to do distance function from xy to y eta. So in laminar steady compressible boundary layer, the least Doronixon transformation is used, which is given by y equal to integration 0 to x rho u ue dx. You can see that this rho e, ue and this dx all is function of x only this. And eta is given by ue upon under 2y integration 0 to y rho dy. So you can see that this part is the function of y, but this y is function of x. So this eta is function of x and y both, while this y was function of x only. And as y was function of x only, then dou y dou y equal to 0. And one more thing, from eta you can see that its limit is 0 to y. So if you want to find this eta at wall, then you have to put this y equal to 0. So this integration will be 0. So it means that eta will be 0 at the wall. Now I already told that f dash is what? U upon u. And this f dash is nothing but this is f dash is function of y and eta. So we are taking one function of y and eta such that u upon e is that function. So now we have u upon u equal to this. Now we will check the transformation. So we have to find dou u by dou y for the ball shear stress. Dou u by dou y we have to find. So we will find what is the derivative dou by dou y. So dou by dou y is nothing but dou by dou y into dou y by dou y plus dou y dou eta into dou eta by dou y. Now we have seen that y is function of x only. So dou y by dou y is 0. So this term will be 0. So what is left? Dou eta by dou y into dou y dou eta. Now we have to find dou eta by dou y. So if you check this, we check this, this u is constant, under 2 eta is also constant. So sorry, u is and under 2 xi is function of x only. Only this part is function of y. So if we are taking dou eta upon dou y, then the integration of this part will be equal to rho, because only this is y is the function of y. So we will get this as ue rho upon under 2 xi dou y dou eta. So if we want to find wall shear stress, dou w, it will be equal to mu dou u by dou y at wall. So we will expand it, mu w, and dou u by dou y at wall, it will be ue, and this rho value will be at the wall. Rho w under 2 xi dou u upon dou eta at the wall. Now you see this function. So this f dash is equal to u upon ue. So if we take dou u by dou eta, so one more thing, this dash refers to the derivative with respect to eta. So if we take dou u by dou eta, it will be equal to dou ue by dou n f dash plus ue f double dash. Now if we take one more thing, at wall velocity u is 0. So if we take eta equal to 0, which is wall, so this f dash xi 0 will be 0. So this first term will be 0 for the wall. So for the wall, only term will be ue f double dash. So you substitute this ue f double dash here. So we will get ue f double dash xi eta w. This term I have directly written xi eta, and here you see ue is 2 times ue square rho w mu w upon under 2 xi. So now at the wall eta is 0. So we can substitute this eta here, and we get tau w equal to ue square rho w mu w upon under 2 xi f double dash xi 0. And the local skin coefficient is given by tau w upon half rho e ue square. So if we divide it by half rho e ue square, rho ue square will cancel and it will come 2 rho w mu w upon rho e under root 2 psi f double dash xi 0. Now in the problem you see the options. So there is also one option of f double dash xi 0, which will be the answer. Is there any doubt in this problem? Mainly, generally you don't have to do all these things much. Mainly if you remember the final rate also, it is okay. Or important is that the CF is directly proportional to f double dash xi eta. This you should remember. So now there is one pretty straightforward question. Compressible boundary layer equations for flat plate involving ODEs, the highest order derivative in which are A. First order, B. Second order, C. Third order, D. Fourth order. So what will be the answer for this problem? Okay, so let's now check compressible boundary layer equations for flat plate, which is given by C F double dash whole dash plus F double dash equal to 0. This is for content equation. Second is C upon PR G dash whole dash plus F G dash plus C UV square upon HE F double dash whole square equal to 0. Oh, sorry, these are momentum energy equation. So here if you expand this term, because this we have to expand all this term because this is the whole dash, so it will be C dash F double dash plus C F triple dash for this term plus F double dash. So you can see highest order is third, so this equation is third order. And second, you can see that this G dash maximum can become G double dash, so, and this will be the F double dash square. So maximum order is second order for this equation. So this equation, so maximum order in compressible boundary layer equation for flat plate is third order. So answer for this problem will be C, third order. One more thing, in the equation you might see one constant C, which is given by rho mu upon rho e mu. So this rho e mu e are properties at edge of the boundary layer, and rho and mu are at a point. So the ratio of these two is called Chapman-Lewinson factor. And the F dash eta is given by U upon UE, and G eta is given by H upon HE. Is there any doubt in this problem? If there is no doubt, then we will move to the next problem. Laminar boundary layer thickness varies approximately as m equal to Mach number at the edge of boundary layer, A me, B me square, C me cube, and D me to the power 1 by 2. So what will be the answer for this problem? So if you have studied lecture properly, you might have listened to that lambda is direct proportional to E square. So as Mach number increases for the edge of boundary layer, the boundary layer thickness also increases. You can think like that if ME is high, then temperature inside the boundary layer will be high, So if temperature inside the boundary layer is high, it means that density is low. So to accommodate the flow with the similar mass flow rate, the boundary layer thickness should be high. So that's why boundary layer thickness increases as ME increases. So option B is the correct one. Was there any doubt in the last problem? Okay, then we'll start with the next problem. Boundary layer thickness at the given value of ME. TAW is adiabatic wall temperature. Option A is approximately the same for insulated plate, flat plate, TW equal to TAW, and cold wall, TW is less than TAW. If more cold for a cold wall, TW less than TAW, than an insulated wall, TW equal to TAW. If less for cold wall, TW is less than TAW, then an insulated wall, TW equal to TAW. Option D is inversely proportional to the wall temperature. So let us talk about boundary layer thickness delta for two kind of wall, cold wall and insulated wall or adiabatic wall. For temperature of cold wall, TW is always less than TAW. So now we will see the two plots. So left hand side plot is for adiabatic wall, it is for boundary layer thickness versus U upon UE, and right, not exactly boundary layer thickness, Y upon X under root REX. So you can find boundary layer thickness from that. And for the right hand side plot is for isothermal wall, where TW upon T is equal to 0.25 for a cold wall. So if you see only the right hand side figure, left figure, okay, someone joined, so I will repeat the problem. I was talking about the problem related to week 4 course, week 4 lectures. So problem is boundary layer thickness at a given value of ME, TAW is the adiabatic wall temperature, is approximately the same for insulated flat plate and cold wall. Option B is more for cold wall than the insulated wall. Option C is less for cold wall than an insulated wall. Is inversely proportional to the wall temperature. So here we have to do a comparison between boundary layer thickness for the cold wall and insulated wall or adiabatic wall. The temperature of cold wall is less than TAW. So what will be the answer for this? So we will see that. So first we will study that what happens to boundary layer profile for adiabatic wall and isothermal wall. So left side is the figure for adiabatic wall and right side is the figure for isothermal wall, where TW upon T is equal to 0.25 and the figure is between Y upon X under root REX and U upon UE. So we can find the boundary layer thickness from this. Whenever U upon UE approaches 1, then that will be the boundary layer thickness. Generally, if it is the approximately 99%, we take that point as boundary layer thickness. So in the left hand side figure you can see that this number which is written in the figure is Mach number. So as Mach number is increasing, boundary layer thickness is increasing. This point you can consider as boundary layer thickness. So as Mach number is increasing, boundary layer thickness is increasing. Similarly for isothermal wall, if you see that as Mach number is increasing, boundary thickness is increasing. And we have also know that boundary thickness delta is that is proportional to m square. Now, if we compare both for the adiabatic wall and isothermal wall, let's take one Mach number, let's say 12. So, for this one, if you consider this boundary thickness will be approximately, you can say that 43, 44 or 42 something. And if you same you take for isothermal wall, for m equal to 12, we'll get its value less than 20. This value I am taking of y upon x under root REX. It is not boundary thickness properly, but it is right proportional to boundary thickness. So you can see that for adiabatic wall, boundary thickness is always greater than isothermal wall. So answer of our problem is very straightforward. Boundary thickness is less for cold wall than an insulated wall. But now the question is why? Because as Mach number increase, boundary thickness increases for both cases, but rate of increment is different. So what happens that there is no heat transfer in adiabatic wall between wall and flow, and for isothermal wall there will be heat transfer from flow to wall. So some of the heat in the isothermal flow will transfer to the wall. There will be heat transfer. So temperature reduces compared to adiabatic wall. So temperature of the in adiabatic case will be greater than temperature in isothermal case inside the boundary layer. So if temperature is high for adiabatic wall case, then its density will be less for adiabatic wall case. So density for isothermal case is greater than density for adiabatic case. Now, if density is yet taking the same mass flow rate, then density mass flow rate depends on density and volume. So if density is mass flow rate is same for the same mass flow rate, if density is less, then there should be more volume. It means that boundary thickness should be high. So for adiabatic wall case, boundary thickness is high. Is there any doubt in this problem?
No, sir. There's no doubt in this problem. But one thing is that I didn't properly get the boundary layer equations, the exact meanings, and what are they for the g function and f function. So I have doubt in that.
You want to ask what is g function and f function?
Yeah, in that entire boundary layer equation. Yeah.
Let's say this is the compressible boundary layer equations for the flat plate, which is given by C f double dash whole dash plus f double dash equal to 0. So here f is nothing but ratio, f dash is nothing but ratio of u upon ue. And if you take the other equation, c upon pr g dash whole dash plus f g dash plus c ue square upon he f double dash square equal to 0. So here in the equation g is equal to h upon he. So like this f and g are defined because we wanted to write the equations. Like generally if we have seen that Navier state equations are partial differential equation. So but it is very difficult to solve the partial differential equation. So we are using these two functions f dash and g, or you can say f and g, to convert those partial differential equations in the ordinary differential equation, because ordinary differential equation is easier to solve compared to this partial differential equation. That's why we are using this way. Is there some other doubt, or you wanted to ask this only?
Okay, so understood. So this F and G are defined in the xi and theta
Huh,
plane,
huh.
not in the xy
Yes, yes,
coordinates.
yes. I think I have
Okay.
explained it later also. Before also, wait. Uh, huh. So, what we do that there is, let's say our equation is xy coordinate, our flow, we convert it to xi and eta. And xi is defined at integration 0 to x, rho e, ue, mu e and dx. And eta is defined as ue upon under 2 xi integration 0 to y rho dy. So these are how we are changing the coordinate system. And the second thing is that we are defining two functions also. F def xi eta equal to u upon ue, and second one is g equal to h upon he, where g is also function of xi and theta. So you can say this is only coordinate transformation in terms of f and g.
Okay. So even for non-similar solutions, the equations will be ODEs.
Equation might not be ODE. Uh, wait, equation might not be ODE, but we uh, we are using this to transform the equations. After that, we take some assumptions like we are taking these two function f and g such that there is some function with if we write the equations, it will come like this, and then we are taking this f and g uh, such that these d ue upon df xi is 0, and d and this dou he upon dou xi is 0. If we do this, then after that you will see that our equations are much more simplified. So mainly we want to simplify the equation. It is not true that we will get the ODE only. Only in the flat plate case we are getting the ODE equation. Other cases there might be partial differential form also there.
So it's an assumption that dou u by dou psi is equal to zero. Occurs.
That we have taken the assumption. We are taking the function such that it is becoming 0.
Oh, okay. So,
And that mainly that this transformation is used because some problem we can simplify using that transformation. Like flat plate case, we can solve it easily compared to that direct Navier-Stokes equations. So any other doubt?
no, sir. I have only a doubt in this. So in any commercial codes also, if for example in any commercial CFD code, this method is only used or direct Navier-Stokes equation method is used.
People directly use the Navier-Stokes equations also. Mainly,
Okay.
it depends on problem to problem also. If some problem is easier to solve this way, then people solve using this transformation and use the transformation and solve. And if it is easier to solve directly Navier-Stokes, then they use Navier-Stokes only. Because sometimes you are solving the both equation using the computational method only. So sometimes the cost of the method also it might increase. It might take more computing power to solve why one method compared to other method. So you have to compare all the possible things and then solve. You might not have that much strong computing power also.
Okay.
So it depends problem to problem. Like similar way, like numerical method which we also use, we do the discretization in numerical method. So that discretization also changes the number of function evaluation which we have to do. So it depends on the many other things also. Okay, then we'll see the next problem. Any other doubt?
No, sir. Everything else is.
The peak temperature within the boundary layer for a cold wall case often increase rapidly with increase in ME, decrease rapidly with increase in ME, varies inversely with ME, varies with under root ME. So first we'll see the temperature profile for both adiabatic and isothermal wall case. That isothermal wall case, let's say it is cold wall and its ratio is TW upon TE is 0.25, and adiabatic wall, so there will be no heat transfer in adiabatic wall case, so dou T upon dou Y at the wall will be 0. That's why it is this profile is perpendicular at the wall, and maximum temperature also will be at the wall, then it will decrease towards the boundary layer. Boundary layer is, and for the isothermal case, there will be heat transfer at the wall. So maximum temperature will not be at the wall but some other location. So the temperature will increase from the wall towards a certain point where there will be maximum temperature, then it will decrease. Now in the both cases, if you see that as Mach number is increasing, this number are Mach number. As Mach number is increasing, the maximum temperature which is at the wall is also increasing. This is for adiabatic case, and for isothermal case also, as the Mach number is increasing, maximum wall temperature is increasing. So the question was also peak temperature also, it increases with the increase in Mach number. So option A is the correct one. And the temperature mainly increase more because the more kinetic energy of flow has, the more it will be converted to thermal energy. That's why the more the Mach number is, the more will be the temperature inside the boundary layer. We'll see the next problem. Reynolds analogy links the following: A, RE and M, B, CF and RE, C, NV and CH, D, CF and CH. So it is a simple problem if you remember the theory that this Reynolds analogy links the CF and CH. So for the compressible flow, the CF will depend on Mach number, Prandtl number, gamma, TW upon TE and IX. And CH will also depend on Mach number, Prandtl number, gamma, TW upon TE and REX. So if we take the ratio of both CH upon CF, it will depend on this parameter, Mach number, Prandtl number, gamma and TW upon TE and REX also. So, and if we, this is for compressible flow. For incompressible flow, it will depend only on the Prandtl number, and it is given by 1 upon 2 PR to the power minus 2 by 3. Even if for the compressive flow, if we consider the CH upon CF with this formula, there will be error of only up till the 2% only. So for rough calculation, you can use this formula also for compressive flow, but not for actual calculation. Next is wall shear stress tau W increases rapidly with ME, decreases rapidly with increase in ME, varies as under ME, varies as 1 upon under ME. So what happens to wall shear stress when Mach number increases? So there are two different things, CF and tau W. We'll see both for both of these. So let's see this one plot which is between CF under root REX and M infinity. So from this plot you can see that this as TW upon TE is increasing, the CF value is decreasing. As TW upon TE is decreasing, then CF value is increasing. And second thing is that as Mach number is increasing, for a particular TW upon TE value, CF is decreasing. So why it happens? First, let's say we have two different TW upon TE. So as there is more so let's say we have two TW upon TE, one is 0.25 and one is 1. So for this case, wall temperature will be lower. If TW upon T is lower, then wall temperature will be lower. So the lower the wall temperature, it means there will be more heat transfer inside the boundary layer. The more heat transfer will be there, the more will be the temperature will be, the more reduction in the temperature will be there inside the boundary layer. So if temperature is lower compared to, so temperature inside the boundary layer for the 0.25 case is lower than temperature inside the boundary layer for 1 case. If temperature is lower, it means density will be high. So if density is high, it means that boundary layer thickness will be low. So boundary layer thickness for the 0.25 case is lower than boundary layer thickness for 1 case. So boundary layer thickness is low for this case. And if boundary layer thickness is low, then the CF value will increase. Why? Because dou U by dou Y value will be high. For the low boundary layer thickness, the gradient of velocity will be high. So if dou U by dou Y is high, it means that CF value is high. So for the low value of TW upon TE, CF value will be high. So in the plot also you can see, for the low value of TW upon TE, CF value is high. Similarly, if Mach number is increasing, it means that temperature is increasing inside. Temperature is increasing. If Mach number is increasing, it means that temperature is increasing inside, because more kinetic energy will be converted to thermal energy. It means that density will decrease. If density is decreasing, it means boundary layer thickness is increasing. And if there is more boundary layer thickness, the gradient will be low. Velocity gradient will be low. And if velocity gradient is low, it means that CF is low. So if Mach number increases, then CF will decrease. But in this problem, it was asked about wall shear stress, not CF. So wall shear stress is given by 1/2 rho e UE square CF. UE can be given by ME square gamma R TE. Sorry, UE square equal to ME square gamma R TE, because Mach number is given by UE upon under root gamma R TE. So we can substitute it. So we'll get half rho e ME square gamma R TE CF. If we take this gamma, if we take this rho e R TE, then from the equation if we state PE equal to rho e R, we can substitute this by PE. So we'll get gamma by 2 PE ME square CF. Now if Mach number increases, CF decreases, but there is also a term of ME square also there. And if we see the value of CF also, with Mach number there is very small change is there. See, value difference is not much. So the effect of ME square will be more in the wall shear stress. That's why when ME increases, this wall shear stress also increases. Is there any doubt in this problem? Now we'll see other problem. That two statements are given and you have to tell which one is false and which one is true. If statement 1, both CF and CH decreases as ME increases. And this statement 2 is both CF and CH increases and wall is cooled. So we have to tell which one is true and which one is false. So we'll come to same plot as before, but this time for CH. And we have seen before that as Mach number increases, CF decreases. Mach number increases and CF decreases. And from the Reynolds analogy, we know that CH and CF behave in the similar manner. So M infinity increases, it means CH also decreases. From the plot also you can see that CH is also decreasing with Mach number. So both CF and CH decreases as Mach number increases. So this statement 1 is true. Now here we have seen before that as TW upon TE is decreased, it means wall is cooled, then CF increases. Similarly for CH, if you see these two plots, here. So low value of TW upon TE means that wall is more cooler. So if wall is more cooled, it means CH value is high. So it means that if we are cooling the wall, CH value will increase. So CH and CF both are increasing at wall is being cooled. So this statement 2 is also true. So option D is the correct one. Is there any doubt? Okay, we'll see the next problem. For a cold wall, TW less than TAW, if QW is the heat transfer occurring at the wall, then option A, QW is less than 0, option B, QW depends on K, thermal conductivity, dou T upon dou N wall, temperature gradient of wall, and the wall area. Option C, QW equal to 0, and option D, QW is greater than 0. This question is also very simple. So one thing is given that there is cold wall and QW is a heat transfer. So if there is wall is cold and flow is hot, then heat transfer will be in which direction? It will be towards the wall, and QW is heat transfer occurring at the wall. So QW will also be greater than 0 because it is occurring at the wall. So QW is greater than 0, rest two options will be wrong, other it is not possible. And this QW at the wall is given by Ka dou T upon dou N. This N is the normal, you can write this Y also, then we have seen dou T upon dou Y, but this N is also normal direction, both are same at the wall. So in which parameter it is depending? K, A and temperature gradient. So option B, if you see that QW depends on K, A and temperature gradient. So this option B is also correct. We will see one plot also for the cold wall. So this is between temperature and normal distance. So you can see that the temperature is high in the middle, somewhere in the boundary layer. So the heat transfer will always happen towards the wall. That's why QW is always greater than 0. Is there any doubt? Okay, then we will see some theory now. So laminar compressible boundary layer equations. So the continuity equation is given by dou u dou x plus dou u dou y equal to 0. X momentum equation is given by rho u dou u by dou x plus rho v dou u by dou y equal to minus dp upon dx plus rho y plus dou y mu dou u by dou y by momentum is given by dou p upon dou y equal to 0. And this is mostly not applicable for hypersonic flow, but okay, if flow is not hypersonic, this is applicable. So let's say this is a boundary layer. If we are moving perpendicular to the our wall, then at every point of that line the pressure will be the same. So pressure is only function of x only, and if everywhere pressure is same, then whatever pressure is here, it will be equal to at the edge of boundary layer. So it is also equal to PEX.
So
Huh?
why in hypersonic regions dou P by dou Y is non-zero? Is it due to the temperature gradient along Y?
It will be mainly due to the high temperature effect also will be there. So it will not be equal
Okay.
to.
So even in supersonic flows, the Y temperature gradient is not very strong. So that's why dou P by dou Y is zero.
Supersonic Supersonic, I don't remember currently, but for hypersonic it will not be there because you might have seen
Okay.
the hypersonic similarity equations and all. So in that also it was there that it will not be equal to that. Supersonic, I don't
Okay.
remember.
So it is mainly due to the temperature variation inside the body.
Huh. Because in hypersonic there will be many multiple kind of effect will be there. Uh, One of the thing will be that on the body this shock layer will be very thin and sometimes bond layer will also merge with that. So flow will be viscous also will be there. There will also will be the uh, chemical reaction will also be possible inside. So that's why it is uh, not possible always.
Okay.
And energy equation is given by rho u dou h upon dou x plus rho v dou h upon dou y equal to dou y k dou t upon dou y plus u dpe upon dx plus mu dou u upon dou y whole square. Here you can see that this rest of the terms are in partial differential form. Only this preferred terms are in uh, ordinary differential. Because this preferred is function of only x. So this derivative we can write this as the ordinary differential. What will be the boundary condition? At the wall there will be no slip boundary condition. It means that u and v will be 0. For the temperature, there can be two type of boundary condition. One is isothermal, other one is adiabatic. If wall is isothermal, then at wall temperature will be equal to wall temperature. If wall is adiabatic wall, then the gradient of temperature at the wall will be 0. Let's say there is some mass transfer happening on the wall with velocity Pw. Then what will happen that V velocity will be equal to Vw. This happens in the case of ablation or transpirational cooling. So based on the type of flow, this boundary condition can also change. And this is at the wall. At the far field, when y is equal tends to infinity, and y tends to infinity, that it means it is infinity, then u will be equal to ue, which is equal to at the edge of boundary layer, and t is equal to te. This tends to equal to the value at the edge of the boundary layer. And there is one transformation called Denison transformation, and in which we transform the coordinate from xy to z eta. Main our aim is to make the profile similarity profile, where xi is given by integration 0 to x rho e ue mu dx, and eta equal to ue upon 2 xi integration 0 to y rho dy. So now we will check the derivative of. We will take the derivative of this dou psi upon dou x equal to, so this xi depends on x only, so its derivative will be similar, simply rho e ue mu e. This is from Leibniz integral formula, and dou xi upon dou y will be 0 because it is not function of x only. Similarly, dou eta upon dou y will be equal to ue upon under root 2 xi rho. Now, if we define the derivative with respect to x, it will be equal to dou y dou x equal to dou y dou eta into dou eta upon dou x plus dou upon dou xi into dou xi upon dou x. Now dou eta upon dou x we have not found till now, so it will directly written dou eta upon dou x, dou y dou eta. Dou xi upon dou x is rho e ue mu e dou upon dou xi. Similarly, dou y can be written as dou y dou xi upon dou y plus dou y dou eta into dou eta upon dou y. And this xi is function of x only, so this term will be 0. And dou eta upon dou y is what? Ue rho upon under 2 xi. Dou y dou eta. So now we introduce a function u upon ue equal to f dash xi eta, where f dash is nothing but dou f upon dou eta xi eta. So we can define the string function which is in y dou phi upon dou y equal to dou u, which will be u we can substitute by ue f dash, and dou phi upon dou x we can define by minus rho v. Now this, if we take this dou phi upon dou y, this f so this equation we found this dou y equal to ue rho upon under root 2 xi dou upon dou eta. So if we substitute phi here, we will get dou phi upon dou y equal to ue rho upon under 2 xi dou phi upon dou eta. And this will be equal to, from this string function, rho ue f dash. Here rho we can cancel, ue we can cancel, then we can get dou phi upon dou eta equal to this, we are taking on the right hand side, under 2 xi f dash. Now if we take the integration of this, so this 2 xi is the constant with respect to eta, and this f dash was also a derivative with respect to eta, so we can directly get this phi equal to under 2 xi f plus k xi, because there might exist one constant which is function of xi only. And at the wall, phi equal to 0. This phi equal to 0, this is phi is equal to some constant, always give the streamline. So and the phi equal to 0 always gives the boundary of one body, which is nothing but wall here. So phi equal to 0. And what will happen for f? F will also be 0. This f is 0 from the b equal to 0. So if you put phi equal to 0 and f equal to 0, we will get k equal to 0. So phi equal to under 2 xi f. We can take similarly other function also, h upon he equal to g eta g xi eta, and the boundary condition for our flow will be, for at the wall y equal to 0, eta will be 0. So our boundary condition will be phi f xi 0 equal to 0, which is for b equal to 0, and f dash xi 0 equal to 0, and g xi 0 equal to gw, which is value of g at the wall. This will be for the isothermal wall. This will be corresponding to T equal to TW at the wall. Okay, sorry for disturbance. Okay, so this G equal to GW is for isothermal wall, which is corresponding to T equal to TW. And for the adiabatic wall, the gradient of this G will be equal to 0. Dou G upon dou eta equal to 0, which is G dash W equal to 0. And when eta tends to infinity, it means y tends to infinity, f dash equal to 1, which is nothing but u upon ue, u equal to ue, and g equal to 1, which is nothing but h equal to he. So if you substitute this f, g, and transform in terms of xi and eta, you will get this compressive boundary layer equation. And here we take that this d ue upon d xi equal to 0, and dou he upon dou xi equal to 0. So we will get this final form of the equations. And in the case of the flat plate, this equation will convert only in the function of eta only. If you see here, this equation, here the derivative with respect to xi alpha exists, and this f dash and g dash is nothing but derivative with respect to eta. So the derivative with respect to xi and eta both exist. But for the flat plate case, only derivative with respect to eta you will find. So that's why this is nothing but ODE equation which you can solve, because this is only in eta. Only one variable is there. And the boundary layer you can find directly. Boundary layer is similar to before only. There is no difference. Only this eta will go away. So what will be the boundary layer? Eta equal to 0, it will be f0 equal to 0 for b equal to 0, f dash 0 equal to 0 for u equal to 0, and g0 equal to gw. This is for isothermal wall, and for the adiabatic wall it will be g dash equal w equal to 0. And for eta tends to infinity, f dash eta equal to 1 and g eta equal to 1, which is corresponding to v equal to ue and h equal to he. So for if you want to solve this for flat plate, it is generally solved using the footing method, in which you assume that value of f, f0, f dash 0, f double dash 0, g0, in which you assume the value of f0, f dash 0 and g0. These three values you assume. Beta, I think it's a mistake. Okay. So if here you see that f0 value you know already. You know the value of f0, f dash 0 and g0. f0, f dash 0 and g0. And you assume the value of f double dash 0 and g dash 0. These two values you assume, and so we are assuming value of these two at the wall, and we try to find the value of f dash eta and g eta, where eta tends to infinity. So if this value is coming equal to 1, it means that whatever we assume is correct. That will be our solution. But if what we have assumed is not correct, then it will not come to this one value. Then we have to update that value. So when we update the value, we can update the value using the Newton-Raphson method or some other method, and then we can keep it repeating it till we get this f dash eta and g eta equal to 1. And these f double dash 0 and g dash 0 is important because you might have seen that for finding the CF also there was term of f double dash 0. So these terms are important for finding those quantities. That's why we use this method. Is there any doubt till now?
So G dash 0 is 0 no, sir, for area particle. So we have that value. Why do you have to assume?
Oh, it depends. Okay. G dash 0 will be, okay. This was for isothermal case. Isothermal case, G dash 0 will not be 0. Okay, so there are two cases. Okay, there are two cases, isothermal case and adiabatic case. So for isothermal case, we know the value of f0, which is 0, f dash 0 and g0. F dash 0 and g0. For adiabatic case, we know the f0 value, f dash 0 value and g dash 0 value. These three values we know. And other two values which we know is f dash eta tends to infinity equal to 1 G eta tends to infinity also 1. But if at the age of only layer. So for shooting method, which I have told before, is for isothermal case, in which we have to assume for G dash 0 and F double dash 0. For isothermal case, for adiabatic case, you have to assume value for G0 and F double dash 0. Only difference is that this G0 and G dash value. Whatever value we don't know, we have to assume that only. Any other doubt?
Okay, sir. Oh.
Okay. If no doubt, then we will see some problem from the previous assignments. So first problem is the correct expression of Mach number is. How is the Mach number given by? A equal to elastic force upon under root elastic force upon viscous force. V equal to under root inertial force upon elastic force. C equal to inertial force upon viscous force. D equal to surface tension force upon gravity force. What will be the answer?
B.
It is B only. Under root inertial force upon elastic force. So Mach number is given by under root inertial force upon elastic force, where inertial force is rho a u square, and elastic force is k into a. K is the bulk viscosity, which is given by rho dou p upon dou rho. So rho and a will cancel out, and it will come under root u square upon dou p upon dou rho. And dou p upon dou rho is nothing but under root dou p upon rho is nothing but speed of sound. So if we substitute it, we will get under root u square upon u square, which is nothing but u upon a. Second problem. The correct expression for compressibility of a gas is A 1 upon rho a square, B 1 upon rho dou v upon dou p, C v dou v upon dou p, D minus 1 upon b dou v upon dou p. What will be the answer? B. Okay, let's say B is here and other. There are multiple possible. Which one?
B and C.
B and C. This one is wrong. Both are wrong. So the
D and A
are correct. So compressibility is given by tau beta equal to minus 1 upon v dou b upon dou p equal to 1 upon rho dou rho upon dou p. How do we got it? This v equal to 1 by rho. So dou v upon dou p will be equal to minus 1 upon rho square dou rho upon dou p. If you substitute this here, you will get tau beta equal to minus 1 upon v into minus 1 upon rho square dou rho upon dou p, and rho into v is 1, so we will get 1 upon rho dou rho upon dou p. And we have seen before that dou rho upon dou p is a square, so it will also come 1 upon rho a square. So option A and D is correct. Specific internal energy of a gas is comprised of following energy modes: A. Vibrational energy, B. Rotational energy. C. Gravitational potential energy. D. Translational energy. So what are the energy modes for the answer?
A, B, and C.
A,
A, B, and D.
A, B and D. And there are other forms of energy also like electronic energy, but it is not present in the option. So let's say there is one gas, it has molecule, so it can move to other places, so it will have translational energy. It can rotate about its own axis, that's why it will have rotational energy. And its molecule can vibrate on its axis, that's why it will have the vibrational energy. Let MHB, MH and MS represent typical Mach number for a hypervelocity, hypersonic and supersonic flow. The correct relation between them is given by which of them?
D.
D is correct one. Because Mach number increases for from supersonic to hypervelocity. Supersonic, it is Mach number greater than 1. Hypersonic for Mach number greater than 5, and hypervelocity is very high Mach number. So that's why MHV is greater than MH is greater than MS. If the pressure change across the expansion fan, oblique shock and normal shock for the same value of M1 is given by PE, PO and PN, then
C.
C. This is also correct. Because let's say there is normal shock and here P is P1, here pressure is P2, and there is oblique shock, here okay, this P1 and P2 and this is P1 . This is normal shock, here pressure is P1, here is P2 and this is oblique shock, here is P1 pressure, here is P2O, and let's say this is expansion fan. I'm not drawing the geometry, but okay. This pressure is P1 here pressure is P2. So one thing is that for oblique shock and normal shock pressure increases, but for expansion wave pressure decreases. So P2N is greater than P1, P2O is greater than P1, and P1 is greater than P2. So the pressure change for the expansion fan will be negative because pressure is decreasing, so it will be the lowest, and from this only fact you can know that C is the answer. This expansion fan pressure will be lowest, change in pressure will be lowest. Second thing, that normal shock, change in pressure in normal shock will be greater than, the pressure in the downstream of the normal shock will be greater than pressure for the oblique shock for the same condition. So the change in pressure will also be greater for this normal shock case. That's why Pn is greater than Po is greater than Pe. Now one question. The molecular weight of a gas is 32 and the ratio of specific heat gamma is 1.4. Its specific heat at constant pressure is. How to find this? We have to find Cp, and we know weight of gas, molecular weight m, and gamma. So Cp is given by gamma r upon gamma minus 1. We don't know the r of the gas, specific gas constant. So we have to find r. How is r given by? R is nothing but ry upon m, where r bar is universal gas constant, which is 8314 joule per mole per Kelvin upon 32. And if we divide it, then we'll get 259.8125 joule per kg Kelvin. Its unit bar for R bar was joule per kilomole per Kelvin. So this is value for R. So Cp will be given by gamma into R upon gamma minus 1. So if we substitute the value in calculator, you will get 909.34 joule per kg Kelvin. So option is the correct one. Next problem. Choose the correct statement or statements related to expansion wave. Flow across an expansion wave is isothermal. It is correct or wrong?
B is
B is correct. Flow across an expansion wave is isentropic. Normal component of velocity decrease across a expansion wave. This is wrong because velocity increases across a expansion wave. Static pressure increases across an expansion wave. This is also wrong because static pressure decreases. Next problem. A gas undergoes a reversible adiabatic compression process such that T1 equal to 1 atmosphere, T1 equal to 300 Kelvin, Tt equal to 900 Kelvin. Find P2. Assume gamma equal to 1.4. How will we solve it?
isentropic.
Because reversibly adiabatic means isentropic. And for isentropic relation, P gamma minus 1 equal to constant. So we can find that T2 upon T1 to the power gamma equal to P1 upon P to the power gamma minus 1. Or we can write P2 equal to P1 did I write something? Yes. Yes, 1 minus gamma.
P2 by P1.
For P2 equal to
hypothesis.
T1 T2 upon T1 to the power gamma upon gamma minus 1. So if we substitute the value, T1 is 1
Option C.
atmosphere. We'll check. T2 is 900, T1 is 300 to the power gamma minus 1, gamma upon gamma minus 1. So it is 3 to the power
Option C.
okay. So answer is 46.76 atmosphere, which is option C. So is there any doubt or question from the classes or anything else?
No.
Okay, then we will stop the class here today. Thank you.
Thank you.